Hello everyone. So welcome to lecture 8. Today we are going to go ahead and cover parametric test assumptions, right? So in the past two classes we had covered the main parametric tests, one sample t-test, independent t-test, dependent t-test, and ANOVA last week, right? And what we did was we just assumed that all of these were the appropriate models. I remember, there's that term kind of junk in, junk out, data in, data, garbage in, garbage out type of thing, right? We can run models on data that we collect and it could just be wrong, right? The answers that we get are wrong because we violated assumptions or we just in fact picked the wrong test, right? So now, as I had promised, we are going to actually go through and we kind of did it a little bit backwards, right? My feeling is that it's more fun to actually do the test and then go ahead and then learn about the assumptions. So, give me feedback. Tell me if you think after this lecture that it would have made more sense to learn the assumptions first. But I think that this is probably a little bit more of a clear-cut way. And I've been wanting to use this joke for a little bit, but you know what they say about assumptions. When you make assumptions, you make a blank out of you and me, right? So let's get going. Okay. So like we had talked about in the past two classes, we had covered parametric tests, one sample t-test, dependent t-test, independent t-test, and one-way ANOVA, right? So this is a good time for you to go ahead and pause. Let's say hypothetically, we had a pop quiz or so, and I asked you, hey, when do we use each one of these tests, right? So pause, and you should be able to go ahead and tell me, look, we use a one sample t-test when we have a known mean that we want to go ahead and compare against, right? Maybe fitness gram values, my class versus fitness gram values, or maybe a standard, blood profile number of HDL cholesterol or something, right? And I want to compare my patients versus the known standard and if there's a difference or not. And you should be able to go ahead and do that for all of the tests that are listed here, right? It's very, very important that you know when to use and why we use each one of these tests, right? Like essentially the scenarios, the different type of scenarios and the different type of examples. So I highly encourage you all to kind of review the last 2 weeks' slides. We're going to be ramping up next class. We're going to start talking about non-parametric tests. And, my hope is that, again, we kind of go cart before the horse. We're gonna go over the tests first, and then I think once you know which tests are out there, then you're gonna really have a good sense of the differences between parametric tests and non-parametric tests and why we would do one versus the other. But to bring it back to today's class, what we are going to go ahead and do now is cover the parametric test assumptions, right? So again, before you can choose one of these tests, we have to meet all of these assumptions, right? Essentially, you can't do this test, any of these tests that are listed above, unless these assumptions are met. And if these assumptions are not met, then you have to do a different test, and that different test would be a non-parametric test. Does that make sense, right? I think that should be pretty straightforward. Okay, so we had covered this before, but all parametric tests have 4 assumptions, right? And the assumptions are normality, that the data is normally distributed, that the data has roughly equal variances, that they are independent of each other. When we sample, that it follows one of the sampling methods that we essentially had covered in, I believe, lecture 3, and that there are no outliers, right? And so today, and each one of these are really kind of analyses in themselves, right? And it's very important that before you go ahead and do any sort of statistical testing, that you really start with test assumptions, right? So, when we're taking the final, we're really going to go ahead and take it from the beginning to the end, right? Where I'm going to give you a scenario, and then the first step you're going to have to essentially do is test for the assumptions, right? Because what happens is, again, if it violates one of these assumptions, then you have to do a non-parametric test, right? So imagine that flow chart that we've been kind of talking about, this mental model. Here is our scenario. What is the hypothesis? You're going to create that hypothesis scenario. Then you're going to go ahead and test the assumptions. Okay, great. All 4 of these assumptions have been met. Then here is our parametric test options, right? If one of these assumptions were not met or the assumptions was violated, then you have to go the parametric, non-parametric route, right? So that's how you have to essentially choose and go back and forth. All right, so without further ado, let's go ahead and tackle normality, right? So I found this figure, and I wish I had this figure a little bit earlier in the semester, because I think it really goes to show what a normal distribution means, not just what it looks like. Like, we know that, hey, look, here's a bell curve, right? And also, by the way, you want to sound really fancy, refer to a bell curve as the glissant distribution, right? Because that's the fancy term, right? So keep that one in mind right over here. So if you go ahead and you'll see that, look, the majority, 50% of the population, fall right smack in the middle, right? Some are a little bit higher, some are a little bit over, but this is the median right over here. Typically also the averages should be very close by unless there are outliers, right? And then you have one standard deviation, or 15% of the population on both sides of the curve, right? Some folks are above expectation, some folks are below expectation, right? And then you have 2 standard deviations where you have your excellent performances and your serious underperformance, right? And you'll see we have our rocket ship and our skateboard riders, right? These are like our overachievers here. This is where I would group you all, by the way, right? You are all above expectation and excellent performers. So let me gas you all up a little, right? But then you'll see this is the normal distribution that we're looking for, right? And in any normal population, this is what you're going to go ahead and expect, right? And we can apply this to anything. If we took all of our heights in our class, for example, right, there's going to be some folks who are really, really tall and then some folks who are really, really short, but the vast majority, 50% of us, would probably fall within a certain category here. So parametric tests assume that each group is roughly normal. So that's the first assumption, right? That when we're picking a test, when we're picking a parametric test, our samples follow this normal distribution, right? And like I had mentioned before, this is known as a glissant distribution, which refers to the degree to which data shows a central tendency and symmetrical distribution relative to the mean. Okay, good. So we're assuming that the data is normal, right? How do we go ahead and diagnose this, right? So, well, the first thing that we can do is we can essentially perform a visual inspection, right? Let's take a pause. What type of figure is this called? Right? Pause. So it should be a histogram, right? We had gone over this early in the beginning, very, very early on. We talked about the importance of being able to do a histogram, and you'll see that, hey, look, this is a normal distribution, right? A very, very clean cut. This is data that's skewed to the right. This is data that's skewed to the left, right? But sometimes, it's not clear, right? When we go ahead, when we have smaller counts, for example, you plot out a histogram and you're kind of like, yeah, I think it looks like a normal distribution, but I'm not really sure, right? So there's a way to go ahead and just not do a visual inspection. And the way that we're going to not do a visual inspection is to use a test called the Shapiro-Wilk test, right? And so we can use a Shapiro-Wilk test to determine if each sample size is normally distributed. And here's the key, right? If the p-value is less than a certain significance level, then the data is likely not normally distributed, right? So let's think about this for a second. We have a p-value, which means, hey, we have to set up a hypothesis statement, right? And our null hypothesis, well, let me go to the next slide. All right, so what we would do, step one, is to go ahead and create a null hypothesis, right? And our null hypothesis is going to be the data is normally distributed, right? And then alternative hypothesis is the data is not normally distributed. So step two would be to run the Shapiro-Wilks test, and let's go ahead now. Excuse me. And we're going to go ahead and jump into SAS with our SAS code. We are going to use the paired data set that we have. Okay, so go back to a previous lecture and download the paired.xlsx data. Let's go ahead and run that. You'll see we have our exam score 1 and our exam score 2. And now this line of code from lines 11 and 12, you'll see that we have this proc univariate and we have this normal command right here. We highlight, we do our running man, and you'll notice that we have lots of statistics right here that's given out. What we are interested in, and notice there's more than one column. If you go back, you'll see that there's lots of info here, right? And then so this first one is for exam score 1, and then when you scroll down, there's exam score 2, right? Remember, our data set had 2 columns of information, okay? Now, there's a lot of info here. It's all very useful, the counts, the mean, right, standard deviation, but what we're really interested in here is the test for normality table, right? And you'll see Shapiro-Wilks here. So let's go back to the slide now. I copied this over, and you run the test, and then now we're going to look at this first column right here, and notice that our p-value is 0.79, right? So since the p-value, 0.789, is not less than 0.05, we fail to reject the null hypothesis, right? We failed to reject this. This means we do not have sufficient evidence to say that the data set is not normally distributed, right? So I know that when we always speak in negatives, double negatives, it might get a little confusing. So let's put it this way. Since the Shapiro-Wilks test shows a p-value of 0.7986, it suggests that the data follows a normal distribution, right? So remember, if this was less than 0.05, if the p-value was less than 0.05, then we would reject the null hypothesis in favor of the alternative, and then the alternative being the data is not normally distributed, right? In favor of the alternative. Now, we had a second column, right? And notice exam score 2. So the question is exam score 2 normally distributed? And let's come down and we look at our Shapiro-Wilks value, and the p-value is 0.035, right? So is the second column, or is exam score 2 normally distributed? That's a question. We'll go ahead and we'll add that to our assignment list. Okay? Good. so far so good. So this is one way to go ahead and test for normality, right? And this actually, in my opinion, is a lot simpler than doing the visual inspection. Although sometimes you just go ahead and you look at it and it's just clearly the case. But this one goes ahead and gives you concrete numbers and math straight to it, right? So there's another way that we can go ahead and test for normality, and that's called the QQ plot. And essentially, what happens is QQ plot is another way to go ahead and perform a visual inspection. It's a little bit better than just looking and seeing if the data is normally distributed. But, generally when you go ahead and you have lots of different ways to kind of confirm normality, the better, right? So again, we're going to bounce back to SAS. We're going to use the paired.data XLSX data just like we did before. Let's go back to the code, and you'll see here QQ plot code, and I'm going to run the proc univariate again, following the normal distribution, and then this time I have some more code here. QQ plot, normal distribution, the mu is an estimate, the sigma is an estimate, and we're going to color it red. Don't worry about that. Just run this code, knowing that, look, essentially we're pointing to the paired data set. That's all that you need to be concerned with. So we do a running man, and now QQ plot for exam score 1. We'll scroll down. QQ plot for exam score 2. And let's take a look, right? So the way to go ahead and interpret this is, 1, do each of these dots, are they going in a linear fashion, right? So if you notice a cluster anywhere, that's not good. If you notice dots way above or way below, that's not good. But if the points follow a linear fashion and they stay close to the line, then that's assuming, it's safe to say that you have normality. Okay, so let's come back. Step 2, interpret the results. If the data points roughly fall along a straight diagonal line in a QQ plot, then the data set will likely follow a normal distribution. The QQ plot appears to be linear here in the 2. Okay, so far so good. Let's go on to the second assumption, right? Equal variance. Parametric tests assume that the variance of each group is roughly equal. The simplest way to test for equal variance is the variance rule of thumb, okay? So this one is also fairly straightforward. What we want to go ahead, what the variance rule of thumb is if the ratio of the largest variance to the smallest variance is less than 4, let me type this out, 4, then we can assume that the variances are approximately equal, okay? So using the paired underscore data dot XLSX, the first step that we're going to do is calculate variance, right? And take a second here and think about this, right? How would we calculate variance for a column? You've done this before in the past, right? We've done this a lot. Just think about this, and I'll give you a hint. How would you calculate means? How would you calculate medians? How would you calculate standard deviation, right? Like we can hand calculate, but how would you do it in SAS? And I think once you see it, it'll remind you. Okay, so let's go back over to SAS. And we're going to go to right over here, lines 19 through 23, assumption 2, equal variance, using the paired data again. Now remember, we have we're going to use proc means, and you see here we have mean, var, but we can put a lot of things, right? We can put n, median, right? But what we're really interested in is just this var, variance, right here. So we do the running man, and now notice exam score 1, exam score 2, median, mean, and now we have our variance, right? And look, variance for score 1 is 160, and the variance for score 2 is 83. Let's come back. we calculate the ratio, so 160.38 divided by 78.12, and that gives us a variance ratio of 2.05, right? Go ahead and punch that into your calculator to check the math. And then we interpret the results. Since the ratio is less than 4, we can assume that the variances between the two groups are approximately equal. Check. Good to go. Perfect, right? Equal variances, second assumption, pretty similar, right? If this number was greater than 4, then we'd have to go ahead and look at non-parametric tests, right? We would violate this assumption right here, but it did not violate this assumption, so we are good to go. And now let's move on. Assumption number 3, independence. Parametric tests assume that the observations in each group are independent of observations in every other group. So, the easiest way to check this assumption is to verify that the data was collected using a probability sampling method, right? A method in which every member in the population had an equal probability of being selected to be in the sample. So, let's say I'm saying example a lot, but let's say our class, FNES 702, that meets on Wednesdays, if I went ahead and randomly just picked your names out of a hat, then we would be good, right? Since I took everybody's survey in this class and everybody was in there, we were good. But if I said, you know what, I'm only interested in the PE majors, or I'm only interested in the dietetics, right, students, and I took only the survey results from the dietetic students, and I ran some statistics, and then I presented it all to you, right, then that would violate this assumption right over here. And think about that, right? Like, we wouldn't be able to generalize those results, right? Imagine if I took the 702 class, right, using our survey as an example, and I said, what do you want to be when you grow up, right? And everybody responded, but then I only took the results from the dietetic students, right? And I said, based off of our survey, the FNES 702 students all want to be, or the majority want to be, dietitians, right? All the PE students would be like, wait a minute, I never said I wanted to be a dietitian, right? So this is where kind of independence comes from, and this is where sampling comes from, right? So examples of probability sampling methods include simple random sampling, stratified random sampling, clustered random sampling, systematic random sampling. Does this sound familiar? I would hope so, right? I think this was lecture 3. So if you're not familiar with the sampling methods, double check. But ultimately, at the end of the day, as long as everybody had an equal chance of being included in your methods, then this assumption is not violated, right? The independence assumption is not violated. If you cherry-picked, it's essentially it. If you cherry-picked data from this one, right, like I only took my tall students and then tried to compare, then this assumption would have been violated, right? So if one of these methods was used to collect the data, we can assume that the assumptions were met. Okay, so let's go into our last and final assumption, assumption number 4, no outliers. An outlier is an observation that lies abnormally far away from other values in a data set. Outliers can be problematic because they can affect the results of an analysis. So, let's think about this again. Let's come back to our FNES 702 class, and let's use our height example. So we're all, roughly about the same height. We all follow a normal distribution right now. But let's say, hypothetically, LeBron James enrolled in our class, right? And now we have somebody who's, 7 feet tall. He's an outlier, right? He now goes ahead and skews our data. And if we were to go ahead and do an analysis on, on our class heights, right, he would really go ahead and kind of throw us all off proportion and throw us out of whack. So it's important that when we go ahead and we check our data, we make sure that there aren't any outliers. And if there are outliers, you then have two approaches to this one, right? You either remove outliers or you go to and perform a non-parametric test, right? So again, there's a bunch of different ways to going ahead and determining whether or not there are outliers in a data set. The most common way to identify an outlier is using interquartile range, right? Remember, we're coming back now to the very, very first lecture now, okay? So refresh your memory on interquartile ranges, but the most common way to identify outliers in a data set is by using interquartile range. If a value is higher than 1.5 times the interquartile range above the upper quartile, Q3, then the value would be considered a mild outlier. Similarly, if a value is lower than the 1.5 times of the interquartile range below the lower quartile, Q1, then the value would be considered a mild outlier. And then same thing goes the other way, right? If a value is higher than 3 times the interquartile range, now 3 times now, this is an extreme outlier. And then if it's 3 times the other way, it is also considered an extreme outlier, right? So when we look at our bell curve, if they are out here and if they are out here, those are outliers on the bell curve, okay? So let's come back. Good. So how do we go ahead and do this, right? So the very, very first step that we want to go ahead and do is to create a box and whiskers plot right over here. Now, let's zoom in. It's very easy. This is actually pretty straightforward. So here we have our box and whiskers plot. Let's review on how we want to go ahead and take a look at this, right? So this rectangle, this blue triangle, that's our mean, or that's our average. This blue line, that's our median. The first line right underneath is the 25th percentile. The line right above this blue, above the median, is the 75th percentile. This bar and this bar are our fences, right? The upper limit fence and the lower limit fence, right? This is almost 2 standard deviations. Anything that's outside of these are considered outliers, okay? So, knowing that, let's go ahead. Let's fire up SAS. I have a new data set here. It's called assumption.xlsx with the sheet name assumptions, and we're going to name this file this work assumptions. And ooh, I have something here I can't run. There we go. I wasn't able to run Running Man for a second. Okay, let's go ahead. I'm going to run lines 28 to 34. Hit our Running Man. Okay, let's take a look at our data. You'll notice that we have one column that indicates team and the other column that indicates points. What we are going to do is we're going to create a box plot. But what we're also going to do on that note is you're going to notice this code here, ODS output. What that does is it essentially saves the data from the box plot out. Okay, don't worry about that, just run the code. Know that the key that you're going to go ahead and change is this one, data equals assumptions, and then the VBox, which is we're going to do points, which is that column name here, points, because we want to know these values here. We want to see if there are any outliers that fall within these values. Okay, highlight, Running Man. And here is our box and whiskers, right? So just a little quiz for yourself. What is this blue triangle? What is this line? What is this line? This line, this line, this line, and then now over here, right? Well, I'll tell you what these two are. These two are our outliers, right? We have outliers in the data. If you pause, just go ahead and kind of answer what these are. And now, this is our average, this is our median, this is Q3, this is Q1. This is essentially 2 standard deviations. up, 2 standard deviations down, essentially, right? And then our outliers. So visually now you're saying, oh, look at this, we have outliers in our data. And then now we're going to go ahead and we're going to view a summary of the box plot data. So let's do a running man here. Notice now it actually goes ahead and tells you 223 and 221, right? These points, these are our outliers, right? Look, the median is 57, the mean is 76, Q3 is 89.5, right? Q1 is 39, 62 is 1 standard deviation, right? So 62 plus 62, that's 12, 100, 6, 12, 62, 62. Why am I can't do the math. Whatever it is, that's 2 standard deviations. And then notice 223, 124 is 2 standard deviations, right? 223. So imagine how far that away is, right? 1 standard deviation is 62. 2 standard deviations is 124. And then we have one outlier at 223, and we have another outlier at 221. Okay, so let's come back. Outlier, our observation. Oh, you know, I don't think I noticed I said this, but an outlier is equal to when an observation is greater than Q3 plus 1.5 times the interquartile range, or when the observation is less than Q1 minus 1.5 times the interquartile range. Sorry, I should have mentioned that before. So let's come back. So the interquartile range is Q3 minus Q1 minus 63 would be 53.5. The upper limit would be Q3 plus 1.5 times the interquartile range, right? So that's equal to 89.5, right? Q3, 89.5, plus 1.5 times 53.5, right? So far, so good. That gives you 169.75. Since 221 and 223 are both greater than 169.75, these are classified as outliers. Therefore, this data has outliers. Therefore, this data violated the fourth assumption, right, of no outliers. And in this case, what I would probably just do is just remove these two cases from them. But in our next subsequent classes, we're going to learn about non-parametric tests, and that'll go ahead and kind of give us different alternatives in the ways that we can go ahead and address these. Okay, so that's it for assumptions. Here's the assignment, right? Using the following data sets, determine if the data meets these assumptions, right, for parametric testing. So what we're going to do for the rest of the time in class now is essentially run through all of these columns, right, these data sets right over here. I'm going to do this one, take this out. So these are the ones that we're going to go, and then for here, use height. And what you're going to go ahead and do is tell me if each one of these are suitable for parametric testing or not. Okay. If you have any questions, feel free to reach out. Otherwise, I will see you all very soon. Thanks, everyone. Bye.